Yes, I have been here for a couple years, and it's nice to get in front of everybody and let you know what's going on at our place. If you've seen my previous presentations, you'll find there are a couple fewer slides with statistics this time around. And for most people, that'll probably be an improvement. So just to make sure, the usual disclaimer, anything that's wrong here is my goof, and NASA, like the rest of the federal government, doesn't endorse any particular product, all the usual stuff. So just briefly, I'll tell you a little bit about where our facility is situated in terms of, why are we there? The NASA Center for Climate Simulation. A little bit about our recent history and what we look like today. A little more detail on some of our science drivers because they have been the things that have caused us to do the new services and the new changes that we've been offering. And then go into a little bit more detail on some of our recent developments, kind of the recent services. We have a new virtualization system, the Advanced Data Analytics Platform, ADAPT. We have some people who are really good at coming up with some of these names. And something that's a little bit related but somewhat different, the Data Analytics Storage System, the DAS. And we will talk very briefly about a little cloud bursting project for the Semi-Arid Carbon Sink project. And then very briefly look at exascale. So NASA has 4 major mission directorates. The Human Exploration and Operations, Launch Services and Space Station come under that. Aeronautics Research, New Vehicle Technologies, Space Technologies, and then the Science Mission Directorate. We have a sister organization, the NASA Advanced Supercomputing Facility that's about 30 miles up the road in Mountain View. They have a large high-end computing center also. It's about 3 or 4 times bigger than ours. They are funded by all of those mission directorates. Our particular facility is located in Greenbelt, Maryland, and we are funded by the Science Mission Directorate, only one of those. Now in the Science Mission Directorate, there are 4 major divisions, the Earth, the heliophysics, sun-related, planetary, and astrophysics. Our funding, more specifically, is virtually all from the Earth science part of that, and not just Earth science, weather, ocean, climate, and not just that, but primarily the simulation end of that, the modeling and prediction part of that. So that's our background. We provide the kinds of high-performance computing, this new ADAPT we will call a local private cloud computing, the data storage and networking kinds of technologies that need to support that kind of science. We have also, as you might imagine, petabytes of Earth science data. A lot of it is simulation data. We have a growing set of repositories of observational data as well. So we try to provide the means for people to collaboratively share their data, publish it, and kind of new and growing our analysis services. As I said, primary customer, Science Mission Directorate. If you're funded by NASA Science, you can likely get an allocation to work on our system or else on our big sister up at NASA Ames. So just a little snippet of an example of some of the simulation science that's enabled. Our biggest customer is the Global Modeling and Assimilation Office. They do a lot of weather and ocean forecasting research. Their flagship model is the Goddard Earth Observing System weather model. They also operate it in a coupled fashion, coupled with ocean models and land and ice. The eye candy on the left side is from a simulation where the grid was approximately 1 mile by 1 mile, so 1.75 kilometers. It took about 30,000 cores. I don't remember exactly how long the simulation took, a long time. This was actually done a couple years ago. They've refined it and they've improved it. But you can see some of the kinds of detail. This is a dust storm over Chad, and you can see the kind of detail you can get from that kind of a high-resolution simulation. Different, but kind of related, is the work that's done by the Goddard Institute for Space Studies. They have a large number of researchers there. A lot of the work that they do on our system deals with exploring climate forcing, so they run much longer simulations. Also, the Land Information Systems folks have models that deal with different varying land types and the inputs from the both from the Weather Service rain gauges and from satellite-borne observations to look at how the land surface evolves. We have a growing use by the NASA carbon research people, both on Discover, which is our traditional HPC system, the large Linux cluster, and increasingly also on the ADAPT system. The Arctic Boreal Vulnerability Experiment above is one of our big customers, particularly on ADAPT. New and related is the High Mountain Asia team looking at changes in glaciers in Asia. The semi-arid carbon sink study, some of this is done on ADAPT, and some, as we'll see later, has been being done on cloud bursting on Amazon Web Services. So with this new focus of supporting the NASA carbon research, a lot of which is observations-based, we have many new data sets, not just our traditional petabytes of simulation data, but now petabytes of observation data. And we're offering new services, some of which we have recently finally stood up ArcGIS, Esri, Geospatial Information System for analyzing and looking at the imagery. We've been able to get very high resolution imagery from the National Geospatial Intelligence Agency and some other sources. And through some innovative things we'll see later, we have some connections to external data at Goddard. Okay. In addition, ADAPT is attracting some other science customers and also a little bit of the engineering crew as well. Planetary defense isn't trying to defend us from other entities on our planet, but rather trying to look at near-Earth asteroids. There's a group that we spun up some virtual machines for, and we would call them the asteroid hunters. That was a fun group. Also, some in our engineering area, support for engineering the calorimetric electron telescope, which is on board the space station. And it's looking at direct measurements of cosmic ray electron spectrum in our galaxy. So those are kind of new areas for us to support. We've always had a variety of science, but it's always been very heavily focused on the atmospheric ocean kind of area. So, if I go the right direction. There's a very brief schematic of the ways we've changed in the last couple of years in particular. On the upper left, the FY15 picture shows our kind of three primary services at that point. Our traditional large-scale mass storage, our very large HPC cluster that we call Discover, and our data portal, data sharing, data publishing services. Those, with the advent of our new ADAPT virtualization system, the data portal and publishing services have now been moved to that platform instead. And we also have this virtualization of, those are persistent services, but we also now have a new set of VMs available for analytics and things like that. So the idea there is, at this point, move the data to the analysis. So that was our FY16 new set of services. For FY17, within a month or two, we hope to finally deploy our data analytics storage service. And it both has HPC-style beefy compute, but also a lot of storage. And the idea there is move the analysis to the data. A little more detail on those particular systems. ADAPT, and you'll hear a little bit more about some parts of ADAPT this afternoon from Scott Sino, who is one of the architects and definitely the implementer. It's designed for large-scale analytics. It's, at least its initial parts were mostly repurposed HPC nodes that were no longer used in HPC. So we've got a lot of hand-me-downs. We do a lot of repurposing. It's intended for loosely coupled applications. The hope was to have a place where scientists wouldn't have to move 3 or 4 terabytes of satellite data onto their local workstation, do some analyzing, then move that off and move 3 or 4 more terabytes for another area and do that analyzing and say, oops, I did something wrong. Now I've got to go, swap that back out and swap that back on. ADAPT has a large storage system. Once again, Scott will be telling you more about some of how that's been put together. And the idea is to have this large area of storage and a number of VMs that people can use to do the analysis. Dirac is our traditional mass storage. We're up to about 65, 67 petabytes of data, mostly simulation data, some observations. We have about a 5 petabyte disk front end. And the traditional HSM back end, it's SGI DMF. Discover is our flagship HPC system, about 3,400 nodes, about 3.5 petaflops at this point, shortly to grow, we hope, about 90,000 cores. New in the last few years is we've significantly increased our scratch space. We have a somewhat flatter hierarchy than some other sites. We don't have campaign storage. We don't have burst buffer. We have scratch space on Discover, which has probably grown about 10x in the last 5 years. And we have our traditional mass storage, and then these new middle spaces. ADAPT is one, and DAS, as you'll see, is another one. DAS is the data analytics storage system, smaller than Discover, and actually in this case we didn't just reuse old HPC nodes, we got some new nodes and petabytes of storage with some innovations on how to make analytics better for the climate, ocean, weather folks. So here's my one statistics slide. The red shows essentially what we've delivered for HPC resources from about 2010, mid-2010 on. The blue jagged line is what we feel comfortable. If you stay at or below that level, your customers are reasonably happy and your management is reasonably happy on utilization. The red is what was actually used. The units there are what we call standard billing units. On Discover, it's roughly not quite 10 core hours for standard billing unit. And the SBU is derived by running benchmarks, real benchmarks of real NASA applications. So when we buy a system, we say, okay, we're adding about this much. So as you can see, the users keep it pretty full. The black line that's on the top is the growth of the mass storage, our traditional HSM mass storage. And if I'd had more time, I would have calculated the slope of the line. But you can sort of see there are kind of 3 different regimes. In the pre-2011, it's growing some. Between 2011 and about mid-2015, there's an uptick. And then with the recent additions and the recent increases in some of the resolution of the work that's going on, you can see that the slope is upticking again. So one question, of course, would be, well, what's driving that? And again, as I said, our biggest customer is the Global Modeling and Assimilation Office at Goddard, and it tends to be that they are running more ensembles of their models and running higher resolution models. Their research simulations tend to be about 10 times finer in the horizontal, each X and Y direction, than their operational. They don't like us to say operational. NASA is not doing operational weather forecasting for the public. That's NOAA's job. What we do is research forecasting. We collaborate closely with NOAA. Some of the technologies both of us share. The GMAO has a mission to take some of the Earth observing satellite observations and turn them into useful things like fields of temperature, pressure, the dust storm as you saw. But we are not the operational, as you all are aware, arm of government forecasting. That said, we do collaborate with NOAA. GMAO does these research model forecasts at a very high resolution and finds that they are, as you might expect, greater fidelity with the actual phenomena that are going on. So on the left in the picture is a picture of the cubed sphere. So that's where you get an idea of the X, Y, Z. That's a way to break up the grid to make it more computationally compatible. That's a bad word, but it's what I can think of. But as that X and Y increases, you can see the number of cores needed to produce a forecast in a timely fashion, and the amount of petabytes greatly increases. We've quickly gotten to the point where data sets are way too big to move, and that we need to think about not storing all the data from each simulation and provide a different approach for doing the analytics. Also, these calculations, these numbers here, are based on just the atmosphere alone. When it's closely coupled with the ocean and with the ice models, you get quite a bit more as well needed in terms of grid points, cores, petabytes. And we didn't even look at memory at that point. So we can't move all this data necessarily to the people that want to look at it in great detail. So one of the things that was developed, as I said, Scott Sino was one of the architects of it, is this advanced data analytics platform, ADAPT. It's kind of a high-performance private science cloud virtualization environment. Most of the part one of ADAPT has been, as I said, reused HPC nodes. Thousands of VMs can be put on our hundreds of nodes. There are two parts of part one, if you will, two sections. One is the persistent data services. That's the data portal, data publishing. And then the other part is the itinerant purpose-built VMs. Some of the above processing goes on there. Some of the ArcGIS processing of the large, high-resolution observational data there as well. The disk is about 15 petabytes of lower-cost commodity storage. Once again, Scott will be telling you more about that this afternoon. We've tried to do kind of a data lake concept. We've got this central disk that's shared. We have data sources. Some are local to ADAPT. Some are transferred from NCCS HPC systems. And Scott and company have implemented an innovative LVFS logical virtual file system. Is that right, Scott? Close enough? Yeah, okay. So basically, it's MODIS data is located at the DAC, maybe a mile away by fiber from our building. So it's at Goddard, but it's a separate data center. And they've developed a nice way to share terabytes, if not petabytes, of MODIS data with ADAPT without actually having to physically copy all the data over. So that kind of concept is part of what ADAPT is about. high-speed internal networks and external networks to these external facilities. And we do have a new Part 2 modular container, and this actually, we borrowed the container. I'm sorry, we didn't borrow it. We repurposed it, but the hardware inside is now new. And this is under development, but going well, and it is OpenStack managed. So just to show you an example of some of our repurposed, that's the outer part of the container. It's a modular container. The guardian there is our watchdog, watch groundhog. Actually, there's one of our systems folks went out there and found that fortunately the groundhog is resident under the container, not really in it. So that's ADAPT. The new system that we hope will be on board in the next month or so is the DAS, the Data Analytics Storage System. The motivation is somewhat similar or largely similar to ADAPT. Like everybody's been saying, data movement is difficult. People want to do analysis. The platform, the HPC platform, isn't always the ideal spot for it. So the approach was to create a true centralized storage, and in this case, move the compute to the storage. So we've got, I believe, close to 20 petabytes of data in the DAS, or the capacity for that. And it is or will be shortly mounted read-write to the ADAPT system, also to the Discover cluster and to mass storage. So the idea is this can be an even larger pool of data that is shared and an environment that is made available for high-speed analytics. Now the new innovation with the DAS is that we are using GPFS as the primary storage underneath, but we're using the Hadoop connector. So the data on the DAS can be either analyzed using more traditional POSIX approach, or you can use Hadoop-like tools to get at it. And one tool in particular that's being developed with folks at George Mason University and others is the Spatiotemporal Indexing Approach, or SIA. And I won't go into great detail, but the idea is to create a query model, because the atmospheric data is all time and basically grid-based. If you have a model that can kind of bridge that time and grid knowledge of your data with the key value-based MapReduce, you can provide powerful ways to analyze the data, both via the older non-Hadoop kind of approaches, or now new through this spatiotemporal indexing approach. So a number of tests have been run, and I'm not going to show the results necessarily, but there are papers that are out there and going to be out there that have shown that this has been very beneficial as a new way to allow different kinds of analytics to be done on both the observational and the model data. So finally, our small foray into cloud bursting using Amazon Web Services. A couple of years back, there was a program called Head in the Clouds that was sponsored by Intel and a couple of others. And we were able to get an award to help us connect to Amazon Web Services and fund a certain amount of the resources there, as well as the ability, I believe, to get the cycle computing for the cloud bursting. And the project that has been done on this is an effort to estimate the woody biomass in sub-Saharan Africa. So what they're trying to find out is just what are the carbon resources that are in trees and bushes there. And what they'll want to do, of course, is watch it over time. How is that changing? So it's based on satellite imagery that is very high resolution. A certain amount of pre-processing is done on ADAPT. The data were sent to AWS and then came back. So we've had good luck with that, but it's, in comparison to our traditional work, it's quite a bit different. So I know we're getting short on time. Just want to look quickly towards exascale. My cloud has disappeared. I'm sorry. We sort of see the analytics and the high computational intensity increasing. We won't be the first folks to be exascale in the government space, but we're closely watching and collaborating. And then I want to say thank you.
Thanks, Ellen. One question for Ellen. We've got one question.
So one of the purposes you described of the DAS was to free up space in the high-performance file system. Well, I noticed that the DAS is only a fifth of the size of the high-performance system, and also you said you were using GPFS. So what about that file system makes it more economical or lower performance or in any way different from the file system on the HPC?
Well, the guy that's the expert is standing up. That's Scott Sino. One quick thing is our HPC Discover Scratch is DDN.
It's DDN based.
Right.
DDN serving up what? GPFS or?
So Discover, Discover, the large HPC has 40 petabytes of DDN HPC storage, GPFS.
GPFS.
Okay, so the back-end storage for the Discover platform are more traditional ready-made appliance kind of units like a DDN or an EMC or whatnot. What we've got, what we kind of prototyped as test of concept and adapt in our DAS or software array back systems, whereas the DAS is comprised strictly of JBODs.
Okay.
Disks presented simply to those. I've come up with a methodology for divvying up that storage, which I'll discuss.
We can't hear you, sorry.
That makes sense.
You have to speak.
All right,
Okay.
thanks.
So the short answer is HPC storage is DDN, a little more expensive than the JBOD storage that Scott will talk about this afternoon. I think the other thing is this is our first instantiation of the DAS. So we don't expect all the HPC data to move there, but we do know that there's data that is a little bit static that's pretty much read-only from the HPC end, whereby if we moved it to the DAS, because it was also being used for other analytics, and it was read-only, then that could free space for new data to go on HPC. So.
Great. Okay, thank you, Ellen.